No, you have to use your own watch, I'm afraid. Yes, that's good. You put that there. Okay, everybody, let's start so that we are punctual and keep to time, etc. I'm very pleased to introduce the next lecture, which is given by two speakers in turn. It's a team effort. And the speakers are Rolf Gademann from Würzburg in Germany, and Allan Green, I think is also from Germany, but affiliated with Complutense University in Madrid. And it's a very interesting talk, I hope, because Rolf is an instrument developer, and so he's not a scientist in that sense. He's an inventor, instrument developer, independent, but also working with Volts in Germany, which produce sort of a photosynthetic measurement kit. Allan Green is well known to many of us. He has an illustrious career as an ecophysiologist, and one of his principal interests, I think I'm right in saying, is the measurement of photosynthesis in lichens using net CO2 exchange, but more recently extensively using chlorophyll fluorescence. And the kit that he uses to measure chlorophyll fluorescence has been developed partly, if not largely, by Rolf. And so we've got this interesting collaboration between an instrument developer and an ecologist. And Rolf has been in the field with Allan in the Antarctic and elsewhere. So, and the title of the talk is Watching Lichens at Work, Chlorophyll Fluorescence in Ecophysiology. So, Rolf, thank you.
Thank you, Peter. By the way, I studied biology and with Otto Lange. It's the same, it's your teacher or whatever. Otto Lange was one of the gods of lichenology, but I went another way. I started to make a second hobby to a profession, and this worked very well. So I met the scientific people. I could talk with them, and I could provide instruments for them without doing the boring work to process all the data okay. But let's start what I put together. With Allan, I came here to your meetings. I think it's the third time, or it's even the fourth time. So I learn a little bit about England here, every time in another town. And last time I was encouraged to give a talk. And this time I even joined in the company. Also I got a membership to the so. And here we have a hotspot for lichen people. And when I say that lichens are normally not seen, if you are looking in a landscape here, normally people don't see lichens. But of course, here perhaps you wouldn't see the other things, but just the lichens. And to see lichens, you have to come closer. And here it's in Edinburgh at a graveyard. And if you look close enough to a stone, you see that lichens form communities. And your job is to look what kind of lichens are around. But you can also ask another question, also what drives this community? Of course, there should be competition between the species, and how does it work? Okay, so lichenologists, as normally you recognize them coming very close with a lens. So it's Ulrich Söchting. It's of Denmark, lichenologist. we met in field trips here in Terra del Fuego. And another way to, the title tells you that we are looking how lichens are working. And one thing is growth, how to measure growth. One idea is you come in front of a glacier. Glaciers are nowadays retracting. And here we are in Fireland, in Terra del Fuego again. And you see the grayish part, that's ice, but covered with silk, with stones. It's not floating anymore. The left part, the white part, is still floating. But in front of these glaciers, there's many area which is has been not covered by plants for several thousand years. And it's obvious that the size of a lichen patch depends on the age. And if you go further and further from the border of the glacier, the patches are getting bigger and bigger. And I think that's a species which is growing quite fast, quite quick. And this picture is nice because it shows that these three patches here, they have the same size. They started at the same time, roughly 30 years ago. And here, and this in our days of measuring automatically, the scientists still have a ruler and a secretary with him and measure diameter, but you have to come back to see a change. Or of course, they did it in the second value they measured is a distance to the front of the glacier, or by looking at old data, you know when this spot was first exposed. And you see that behind starts a young forest to grow. Okay, but another way to measure, which is more what I like, a bit of electronics, and in chlorophyll fluoresces, not only in UV light, but in any light, with a deep red color. And this was Kautsky first, who thought or find out that it's related to photosynthetic activity. And here you have two types of single-cell algae and of a tissue. One's illuminated with normal light, white light, and the other with UV light. As even with white light, there is behind maybe 5% of this red light, of this red fluorescence, but we can't distinguish it. And but what came out that if you illuminate a sample, it starts with bright red light, and after a few minutes it dims down, and it came out that when the electronic transport chain is filled up and energy is not used in a Kelvin cycle, for example, then it feeds back and dims the opposite. The light which is not used comes as a fluorescence, at a high fluorescence. But when it's then used, if the whole chain starts to work, the Kelvin cycle starts to fix CO2, then it competes with this color and it dims the light down. And you can, okay. That's what we are doing. We are measuring this red light, but applying a special trick to having modulated light pulses sitting on top of other lights. And so we, okay, here I have a special tool with light. Also with no light, there's no fluorescence reading in over here. Then we got a signal, fluorescent signal, and we can apply a very high light of several thousand to 3,000 times the sunlight to saturate the whole system. And then the limitation or the competition with the light which goes to the photosynthesis doesn't count anymore. And so we get a saturation and get a maximum. So we have any time an absolute measure. And now if we apply any constant, quite ambient light, which also can come from our instrument, then you see the so-called Kautsky effect. Highlight in the beginning and then starting to use the energy, and it drops down the fluorescent signal. Okay, what can we do with this? I can put this instrument on a dry lichen. Oops, sorry. And you see here I've watered the lichen, and fluorescence starts to rise and to develop this saturation curve. Also in our instrument, we select two fluorescent signals, one with ambient light and one with this saturation trick. And so the only thing what's in our experiments counts is this developing fluorescence and developing such a yield, a high value. And this tells us the lichens are active. And so with small instruments, I developed once a pocket pump where you can test for actual activity, or this micro pump here, which we screw on a tree or on a rock. Here, this could be sit on a rock and point on a lichen, and then with the help of a data acquisition system which provides power and which sends the data via satellite to home, to a database, we can track down how long the lichens are active. And normally it's enough to know how long they are active and not how much they are active. And this is Claudia Colesi of setting up at a little microhead in the Tainish of Scotland, also on the sea level. The challenge for our instruments was a permanent high humidity. Antarctica is much easier. Cold, dry weather doesn't hurt the electronics. I was lucky to, when I did my studies with Otto Lange, I did a PhD, I met Uli Schreiber. He is one of the leading scientists to see how photosynthesis is working. But it was 40 years ago, and I started to work with him. My thesis never was finished, but I had an income for my life. And the company Walz, also Otto Lange developed a lot of instruments. He was working with gas exchange instruments, and then came Uli Schreiber. Otto Lange gave his knowledge to the company. Uli Schreiber did another way. He kept the knowledge with independent developers, and the company just manufactures and sells the instrument. And this came out to be perfect. So we have still an income, even if I'm sitting here or doing a cruise in Terra del Fuego. And so I just recommend to do my way. Okay, but now I think I'm exactly in the time. Alan, come on the stage here. Ta-ta, ta-ta. Yeah,
So we need the next projection. This always happens to me. It doesn't matter. It's my love-hate relationship.
okay, and the snow it wasn't.
Oh, here I am. That's even better. Come on, keep it up. As you can see, it is actually possible to make money from lichens. Not many of us achieve it.
You need to stand in front of the mic.
Oh, yeah, stand in front of the mic, yeah. Okay, over up. Good, here we go. So my job is simply to give you an example of how you can use this particular machine here to do studies which you possibly can't do yourself very easily. And so I decided to just talk about looking at lichens under snow. And you know, it's not very easy to study lichens under snow because if you go under the snow, you disturb it. So what I'm going to go through here, this is a research site with the fluorescent heads here at Cambridge Bay in the Arctic. And this is what it's like in the winter there. That's the snow, and about minus 24 degrees. I think the average temperature in January is minus 24 degrees, so it's a cold place. And then this is another one here in Scott Base in Antarctica. You can see this is in summer, minus 5 or 0 degrees. And in winter, there's the same place with the snow. Now, you notice there's not a lot of snow there. Sort of draw attention to it. Now, what do we expect to happen here? Now, if you're worked in the lab, you can detect photosynthesis by lichens down to minus 20 degrees centigrade. So there's a good possibility that something should be happening underneath this snow. So the idea of this machine, which measures the chlorophyll fluorescence and gives you activity, it gives you the light level, it gives you the temperature, it gives you the humidity, and it sends it to you by satellite, so you can do it from your desk at home and watch what's happening to the lichen down in Scott Base. You know, so what happens? So you get the snowfall. So this is a simple graph. The top graph is simply the light above the snow, and the bottom graph is the light at the lichen level. And you can see at the arrow point there it snowed, and the light disappears. And this is my first surprise. We never see any light under the snow. There's lots of discussions about how much light gets through the snow, and the machine says none. Even with that little bit of snow at Scott Base. But the great thing about this is that this is a wonderful signal because it tells you when it snowed. So when the light disappears at the lichen, you got your snow there. It's nice and simple. So that's your signal. So the light becomes the best guide as to when snow is present. So now we go and look at temperature here. Now the top graph there is the same one. There's the blue lines are where the light of the snow, and then it disappears. And the dashed black line is actually accumulated snow amount above the lichen. And down below, the bottom, there are two lines. There's a red line, which is the temperature of the lichen, and there's a black line, which is the temperature of the air above the snow. And everybody says that snow insulates, and the answer is correct. You can see that the red line there is quite stable. It falls a bit, and the air temperature there is down to minus 24, but the lichen temperature only goes down to about minus 8 there, and it's relatively stable. So the first thing you can say is, yes, snow insulates. Now, this is where everything goes wrong, because everybody starts talking then about how it protects it from what happens outside. But this is irrelevant. It's more like a house. you insulate your house, and then you put a heater inside the house and warm it up and get your temperature there. So the temperature under the snow is controlled by the surface under the snow. So we can move on to this here now. And you can see the phases here. The start there, the blue line at the bottom shows you where the light was, and that disappears. And then you get the same red line for the lichen. And at the first phase there, the lichen equilibrates its temperature with the surface of the snow, with the surface of the soil. And in Cambridge Bay, it's sunny some of the time, so it's a little bit warm. But then after a day or so, it starts to equilibrate with the bulk soil temperature down below. And the permafrost is at about -8 degrees and there. So after 2 or 3 days, it's gone down to -8 degrees because that's the temperature of the permafrost there. And it's the temperature of the soil that drives the temperature of the lichen, and nothing much to do with anything that happens up above in the air, which you can see is fluctuating all over the place. So that's the first message there. So, oops. How did I do that? So the next question is, what about the activity then? You know, it's nice and simple. So the bottom graph is the same graph with the red line, the lichen, and the black line, the air. And up above is the fluorescence yield from one of these things here. And when you've got a black line on that graph, you've got activity. And you can see the first part there, it's very bumpy because you get activities changing through the day as the sun goes up and down each day. And then the snow falls, and suddenly you've got almost stable activity there. They're active. And it stays active, and then suddenly it stops there. And it stops there at about -4 degrees centigrade, thereabouts. And then no more activity after that. It's quite simple. So when the temperature falls underneath the snow, the lichen seems to stop its activity at some point. So why is that? And it happens because there's a special relationship with the air humidity when ice is present. When ice is present, water is in a solid state, and so it has a lower energy activity than when it's in a liquid state. And the water in the lichen is in a liquid state inside the alga. It's always liquid inside the alga and the lichen. And so when the temperature falls under the snow, and that's just this thin black line here, the theoretical line, as the temperature falls, the relative humidity under the snow falls. So when the temperature is 0, it's 100%. And when you get down to get my eyes working here, -20 degrees, you're down to about 80% relative humidity. So under the snow, you get development of a drying environment as the temperature falls. I think this is known as freeze drying. Oh, yes, I've heard of that somewhere else around the place. It's a very common technique. So that blue line there is actually the humidity measured by one of these things. And you can see it follows the theory almost perfectly there. So as the temperature falls under the snow, the humidity falls, the lichen dries out, the lichen stops being active. It's quite simple because it's desiccated. So it's not actually, it's sort of due to the temperature, but it's one step away from it. It's through the humidity under the snow. None of this, as you can see, has got anything to do with what's happening up above the snow. It's totally irrelevant what's there. So when does it stop? That's the next question. So here's some data. Now, we've been running these things for years. So here's 6 sites here. The first 2 sites are polar sites, one at Cambridge Bay at the Arctic Circle, and one that's got base well inside the Antarctic Circle, that deep Antarctic. That's site 1 and 2 there. And then we've got 2 alpine sites in Austria, one at 3,000 meters and one at 2,500 meters. And then we've got 2 sea level sites, one on an island off Sweden and the other one on a little hill in Germany. So we've got a more temperate site there. So we've got records for all of these in the last few years. So we can have a look and see, when do they stop being active? And this table here, on the left is the name of the sites, the 3 sites, Scott Base, Cambridge Bay, the polar ones, and then the higher Hoher Sonnenblick, the high alpine one, And then you have the mean temperatures for those places, minus 19 in Scott Bay, the annual mean, minus 12 Cambridge Bay, and minus 4.5 in Horizontal. Now, then you have a list of species that are being monitored at each site. The red ones are bryophytes, are mosses, and the black ones are lichens. And then down here, you have the stop temperature at each place. And the astonishing thing about this is the stability of this temperature. It's always -4, -5. That's it. All these sites, it's exactly the same. Doesn't matter if it's a moss, doesn't matter if it's a lichen, doesn't matter where it is at -5 degrees, it's stopped. If we go to the other sites, then they obviously have warmer soils. If you look at the temperatures at the side there, that's the temperature, mean temperature being measured. They're all well above -4, and they remain active under the snow. So they don't stop because they don't get to -4 or -5 degrees. And so I can summarize this at the end, that lichen activity stops at -4 to -5 degrees. And not even that, better than that, it's the same for lichens and mosses. And even better than that, it's the same everywhere. So as a plant ecophysiologist, I can't believe I found something that applies everywhere. It's a real surprise to me, but there it is. And so what actually drives the whole system is the temperature, bulk temperature of the soil, because you're dealing with the insulated area inside. Now down at the bottom there is a little graph. So the red line, I think, is temperature. Yeah, I think it might be. And the black line is activity at Scott Base for 2 years. We have a machine down there. There's a solar panel and a battery. It's been running for 4 years now. 2.5 million data points from this machine. Takes a reading every 30 minutes. Has not yet missed a reading. No one has put a hand on that machine since it was put in. It just sits there. I can go to my office. I can dial up the computer and see exactly what's happening in Scott Base 10 minutes ago or 20 minutes ago. You know, so it's a fantastic system. And one thing it has done, it's answered the question of what happens under snow. And the answer is, in the polar regions, you can see mostly nothing. And in the temperate regions, yes, and that's the danger zone. Because if they're active under snow with no light, bad news for them. And then you get lichen kill around the place, which is a known phenomenon in the high alpine areas. Great, thank you.
I'm afraid we have no time for any questions, so maybe you can speak to the speakers after the session. I would like to invite Faye to introduce other speakers. Next speaker.
Next, we have a series of 3 talks, all about the use that people have made of the interactive maps, and looking at how it's changed, how people record and look at lichens. We've got 3 speakers, and my intention was always that we would listen to the 3 speakers, and then if there's time for questions, we would ask questions to the panel of 3. In actual fact, our first speaker is Anne Claypole, and she's had an injury, so she's not going to be able to make it today, but she has recorded her talk. So we will listen to Anne Claypole, and then I'll invite Cassie Laughlin to come and talk to you. And by contrast to what you're going to hear from Cassie, who can recognise 1 lichen, you're then going to hear from Neil Sanderson, and I've lost count of how many he can recognise, but it's got to be a 4-figure sum. So I hope you enjoy these talks, and we'll start with Anne Claypole's. Thank you.
Ladies and gentlemen, they say you will never forget your first time. And I'm going to tell you why. The database, with its species distribution maps, is the heart of the BLS. Without it, we're nothing more than a bunch of stamp collectors. However, its offspring, the interactive map, is the most powerful tool we have at our disposal. When we were blessed with it almost exactly a year ago, it was declared the best thing since sliced bread, a game changer, inspirational, a paradigm shift in British lichenology. So if the database is our treasure trove, then the interactive map gives each and every one of us instant access. It has all the qualities of the perfect teacher. It informs what has been found, where, and where not. It motivates with feelings of guilt and responsibility.